Imagine the universe as a grand cosmic kitchen and stars as the main course. Tonight, we're whipping up a stellar feast, and we're starting with the ingredients. Nebulae, vast clouds of gas and dust where stars are born. These aren't your average kitchen ingredients, though. They're the remnants of ancient stars, recycled and ready to create something new. But don't worry, we won't be cooking up a supernova just yet. First, we'll take you on a journey from these humble beginnings to the explosive finale, showing you the incredible life cycle of stars. So, grab your apron. Well, maybe not an apron, but definitely your curiosity, and let's dive in. You won't want to miss a single bite of this cosmic tale. The cosmic cradle. What is a nebula? In the vast, dark canvas of space, nebulae are the celestial artists, painting the cosmos with hues of pink, blue, and gold. These interstellar clouds of dust, hydrogen, helium, and other ionized gases are the birthplaces of stars, a cosmic cradle where the universe nurtures its newest family members. Nebulae are often the remnants of dying stars, or the scattered material that never quite formed into stars in the first place. They are the recycling centers of the universe, where the stuff of old stars is repurposed into new ones. Think of them as the universe's way of hitting the cosmic reset button, taking the ashes of the old to create the new. Nebulae come in a variety of shapes and sizes, each one unique, like snowflakes. Some are vast and diffuse, stretching across light years, while others are small and dense, barely visible against the black backdrop of space. The most common type is the diffuse nebula, which can be further divided into emission, reflection, and dark nebulae. Emission nebulae, like the famous Orion Nebula, glow with their own light. Their gas is heated by nearby stars. Reflection nebulae, on the other hand, shine by reflecting the light of nearby stars, like a cosmic mirror. Dark nebulae are the shy ones, absorbing light and appearing as dark patches against the brighter background. The life cycle of a nebula is a dramatic tale of creation and destruction. It begins with a molecular cloud, a dense region of a nebula where gravity slowly pulls the gas and dust together. As the cloud collapses, it heats up, and if it gets hot and dense enough, nuclear fusion ignites, and a new star is born. This process can take millions of years, a blink of an eye in cosmic terms. Meanwhile, the remaining material can form a disk around the new star, which may eventually clump together to form planets, asteroids, and comets. It's a cosmic ballet, a dance of creation that has been playing out for billions of years. Stellar nurseries, where stars are born. In the vast, dark expanses of the cosmos, there are places where the universe breathes life into the cold, empty void. These are the stellar nurseries, vast clouds of gas and dust where stars are born. Think of them as the cosmic equivalent of a bustling city hospital's maternity ward, but instead of doctors and nurses, the main players are gravity, gas, and dust. The primary components of these nurseries are hydrogen and helium, the lightest and most abundant elements in the universe. They also contain traces of heavier elements, remnants of previous generations of stars that have lived and died. These nurseries can be massive, stretching across hundreds of light years, and they can contain enough material to form millions of stars. The process of star formation begins when a disturbance, such as a nearby supernova explosion or the collision of two clouds, causes a region within the nursery to collapse under its own gravity. As the cloud collapses, it breaks up into smaller, denser clumps. These clumps continue to collapse and heat up due to the conservation of angular momentum, forming what are known as protostars. Protostars are not yet stars. They are still in the process of forming and are not hot enough to initiate nuclear fusion. They are often enshrouded in a cocoon of gas and dust, making them difficult to observe in visible light. However, they can be detected in infrared and radio wavelengths, which can penetrate the dusty cocoon. As the protostar continues to collapse, it spins faster and heats up. When the core reaches a temperature of about 10 million degrees Celsius, nuclear fusion begins. Hydrogen atoms start to fuse together, forming helium and releasing a tremendous amount of energy. This is the moment when a protostar is born as a main sequence star, the most stable and long-lived phase of a star's life. The star will continue to shine, fusing hydrogen into helium, for millions or even billions of years. Meanwhile, The leftover material from the formation of the star can coalesce to form planets, asteroids, and comets, creating a solar system. This is how our own sun and solar system formed, and it's how stars and solar systems are formed in stellar nurseries throughout the universe. It's a testament to the cycle of life and death, creation and destruction, that is the hallmark of the cosmos. The role of gravity in star formation. In the vast cosmic dance of the universe, gravity takes center stage, orchestrating the birth and life of stars. It's the invisible puppeteer, pulling strings that shape the fate of celestial bodies. Stars begin their journey as nebulae, colossal clouds of gas and dust. These clouds, scattered throughout galaxies, are the cosmic nurseries where stars are born. Gravity is the midwife, coaxing these diffuse clouds into the dense, compact bodies we recognize as stars. Think of a nebula as a loose gathering of cosmic dust and gas, like a dandelion seed head waiting for a gust of wind. Gravity is that wind, pushing and pulling the particles together. As the cloud contracts, it grows denser and hotter. This is where gravity's role becomes even more crucial. It's not just pulling particles together, it's setting the stage for nuclear fusion, the process that will define the star's life. The more massive the cloud, the more gravity pulls it together, and the hotter and denser the core becomes. This is how gravity determines the size and type of star that will emerge from the nebula. But gravity doesn't just bring particles together, it also sets them spinning. As the cloud contracts, conservation of angular momentum causes it to spin faster. This is similar to how a figure skater spins faster as they pull their arms in. This spinning can cause the cloud to flatten into a disk with a bulge at the center. This bulge is the protostar, the precursor to a star. The protostar continues to pull in more material from the surrounding disk, growing denser and hotter. Eventually, the core becomes so hot and dense that nuclear fusion ignites, and a new star is born. Gravity, the cosmic architect, has once again crafted a new celestial body, ready to shine for millions or even billions of years. Protostars, the early stage of a star's life. In the vast cosmic nursery of a nebula, where gas and dust swirl in a mesmerizing dance, the journey of a star begins. This is the realm of protostars, the embryonic stage of a star's life. Picture a cosmic seed, nestled within a dense cloud of molecular gas, primarily hydrogen, with a sprinkling of helium and a dash of heavier elements. This seed, drawn together by gravity, starts to collapse in on itself, much like a cosmic snowball rolling downhill, gathering more material as it goes. The temperature and pressure at the core begin to rise, setting the stage for the dramatic transformation that will eventually give birth to a star. As the protostar continues to feed on the surrounding gas and dust, it grows denser and hotter. It's like a cosmic teenager, growing rapidly and undergoing significant changes. The increased pressure and temperature at the core trigger nuclear fusion, but not quite yet. This is a crucial point in the protostar's life. It's not yet a star, but it's well on its way. The protostar is now a ball of gas, glowing faintly due to the heat generated by the gravitational contraction. It's like a dim, cosmic light bulb, slowly warming up. The protostar phase is a critical period of growth and development. It's during this time that the protostar gathers most of its mass. However, this process isn't always smooth sailing. Sometimes, the protostar might eject some of its material back into space in powerful jets, a bit like a cosmic temper tantrum. These jets, known as bipolar flows, can be quite spectacular, stretching out for light years. Despite these outbursts, the protostar continues to grow and evolve. It's a testament to the dynamic and often turbulent nature of the early stages of a star's life. Once the core temperature reaches a critical point, typically around 10 million Kelvin, nuclear fusion of hydrogen into helium will ignite, and the protostar will officially become a main sequence star, marking the end of its protostar phase and the beginning of its stellar adulthood. Main sequence stars, the prime of stellar life. Stars, much like living organisms, have a life cycle, and the main sequence phase is the vibrant, productive middle age of a star's life. This is where stars spend the majority of their time, fusing hydrogen into helium in their cores, a process that releases an enormous amount of energy. Our sun, for instance, is a main sequence star, a G-type main sequence star to be precise, and it has been in this phase for about 4.6 billion years. It will likely remain in this phase for another 5 billion years or so. Main sequence stars are the stable, reliable workers of the universe, steadily converting hydrogen into helium, shining brightly, and maintaining a delicate balance between the inward pull of gravity and the outward push of radiation. The main sequence is a specific band on the Hertzsprung-Russell diagram, a scatter plot that shows the relationship between a star's brightness and its color or temperature. Stars on this band are in a state of hydrostatic equilibrium, where the force of gravity pulling inward is balanced by the force of radiation pushing outward. This equilibrium is crucial for a star's stability. It's like a cosmic balancing act, a dance between two immense forces. The more massive a star, the shorter its main sequence life. This is because massive stars burn their fuel much faster, like a sports car burning gasoline versus a sedate sedan. For example, a star with the mass of our Sun will remain on the main sequence for about 10 billion years, while a star with 10 times the Sun's mass may only last a few tens of millions of years. The color and brightness of a main sequence star are determined by its mass. The most massive stars are blue and extremely bright, while the least massive are red and dim. Our Sun is a yellow dwarf, a term that might sound unimpressive, but it's a testament to the Sun's stability and longevity. The temperature of a main sequence star's surface, or photosphere, ranges from about 400 degrees Celsius for the coolest red dwarfs to over 30 degrees Celsius for the hottest blue giants. Despite these extreme temperatures, the surface of a main sequence star is relatively calm compared to other types of stars. They don't exhibit the violent eruptions of red giants or the explosive behavior of variable stars. Instead, they shine steadily, providing a stable environment for any planets that might be orbiting them. The main sequence phase is also where stars do the bulk of their work in terms of nucleosynthesis, the process of creating heavier elements from lighter ones. This is where the carbon, nitrogen, and oxygen that make up a significant portion of our bodies were forged billions of years ago in the cores of main sequence stars. It's a humbling thought, a reminder of our cosmic connections. When a main sequence star runs out of hydrogen in its core, it begins to evolve off the main sequence, starting the next phase of its life cycle. But that's a story for another time. For now, let's appreciate the main sequence, the prime of stellar life, where stars shine brightly and steadily, playing a crucial role in the universe's grand narrative. Nuclear fusion, the engine of stars. In the vast cosmic forge, stars are born, live, and die in a spectacular display of nuclear alchemy. At the heart of this stellar drama lies nuclear fusion, the engine that powers stars and forges the elements that make up everything we see around us. Picture a star as a colossal, self-sustaining nuclear reactor, where hydrogen atoms are squeezed and heated until they fuse into helium. This process releases an enormous amount of energy, which is what makes stars shine so brightly. It's like a cosmic version of a campfire, but instead of wood, the fuel is hydrogen, and the flame is a searing plasma that can reach temperatures of millions of degrees. The fusion process doesn't stop at helium. As stars age, they begin to fuse heavier elements. In the core of a star like our Sun, hydrogen fusion will eventually give way to helium fusion, creating elements like carbon and oxygen. This is akin to a chef layering flavors in a complex dish, with each new element adding a new dimension to the stellar recipe. The exact path of fusion depends on the star's mass. Massive stars, for instance, can cook up elements all the way up to iron. But here's the catch. Fusing elements heavier than iron doesn't release energy, it absorbs it. It's like trying to light a wet log. It just doesn't work. When a star runs out of fuel for fusion, it can no longer counteract the inward pull of its own gravity. For massive stars, this leads to a cataclysmic supernova explosion. In this final act, the star's outer layers are blasted into space, seeding the cosmos with the heavy elements forged in its core. It's a dramatic end, but also a generous one, as these elements become the building blocks for new stars, planets, and even life itself. In a very real sense, we are all stardust, the remnants of ancient stars that went supernova. This cycle of creation and destruction is the lifeblood of the universe, driven by the incredible power of nuclear fusion. The Hertzsprung-Russell diagram, mapping stellar evolution. In the vast canvas of the cosmos, stars are born, live, and die in a grand cycle, much like the seasons on Earth. To make sense of this stellar life cycle, astronomers use a powerful tool called the Hertzsprung-Russell diagram, often affectionately referred to as the HR diagram. Picture it as a cosmic map, guiding us through the evolution of stars. This diagram plots stars based on their luminosity or brightness and their temperature, creating a scatter plot that reveals the stages of stellar evolution. It's like a family tree for stars, showing their relationships and how they change over time. The HR diagram is divided into distinct regions, each representing a different stage in a star's life. On the horizontal axis, we have temperature, with hotter stars on the left and cooler ones on the right. The vertical axis represents luminosity, with brighter stars higher up and dimmer ones lower down. Most stars fall into a diagonal band called the main sequence, where they spend about 90% of their lives fusing hydrogen into helium in their cores. Our Sun, for instance, is a main sequence star, comfortably nestled in the middle of this band. It's like the stellar equivalent of a steady, reliable job. Nothing too flashy, but it gets the job done. Above the main sequence, we find the giants and supergiants. These are stars that have exhausted the hydrogen in their cores and have swollen to enormous sizes. They're like the retirees of the stellar world, having left their main sequence jobs and entered a new phase of life. Some of these stars are so large that if they were placed where our Sun is, they would engulf Earth and the inner planets. Below the main sequence, we have the white dwarfs, the remnants of stars that have shed their outer layers and are slowly cooling down. They're the quiet, unassuming end to a star's dramatic life. The HR diagram also helps us understand the life cycles of stars. A star's journey begins in a nebula, a vast cloud of gas and dust. Gravity causes the cloud to collapse, and as it does, the material at the center heats up, forming a protostar. This is like the embryonic stage of a star's life. As the protostar grows hotter, it eventually reaches a point where nuclear fusion can begin, and a new star is born on the main sequence. The star will spend millions or even billions of years in this stage, depending on its mass. More massive stars burn through their fuel more quickly, like a sports car guzzling gas, while less massive stars are more fuel efficient, like a hybrid car. Low-mass stars, red dwarfs, and their life cycles. In the vast cosmic ocean, stars are the luminous islands that the darkness. Among these celestial bodies, red dwarfs are the most common, yet they often go unnoticed due to their dim nature. These low-mass stars, with masses ranging from about 0.8 to 0.6 times that of our Sun, are the quiet achievers of the universe. Their life cycles are slow, steady, and incredibly long, making them the tortoises of the stellar world. Red dwarfs begin their lives in the same way as any other star, from a collapsing cloud of gas and dust called a nebula. Gravity pulls the material together, and as the cloud contracts, it heats up. When the core reaches a high enough temperature, nuclear fusion ignites, and a new star is born. For red dwarfs, this process is slow and steady, like a simmering pot on a low flame. Their low mass means they burn their fuel slowly, a trait that grants them an incredibly long lifespan. In fact, red dwarfs can burn for trillions of years, far outliving any other type of star. As red dwarfs age, they go through a process called the main sequence phase. This is the most stable part of a star's life, where it shines steadily, fusing hydrogen into helium in its core. For red dwarfs, this phase can last for an astonishingly long time. Our Sun, for comparison, has been in its main sequence phase for about 4.6 billion years and will remain so for another 5 billion years. But a red dwarf with half the mass of the Sun could remain in its main sequence phase for over 100 billion years. That's longer than the current age of the universe. When a red dwarf finally does run out of hydrogen fuel, it doesn't go out with a bang like its more massive counterparts. Instead, it slowly fades away, turning into a white dwarf. This is a dense, Earth-sized remnant of the star that slowly cools over trillions of years. It's a quiet, unassuming end to a star that has seen the universe age around it. In the grand scheme of things, red dwarfs are the ultimate survivors, outlasting all other stars and bearing witness to the slow evolution of the cosmos. They may not be as flashy as supernovae or as massive as blue giants, but their longevity and commonality make them a vital part of the stellar ecosystem. Medium-mass stars, the life and death of sun-like stars. In the vast cosmic kitchen, stars are the chefs, cooking up the elements that make up everything we see around us. Medium-mass stars, like our very own sun, are the reliable home cooks of the universe. They don't explode in dramatic supernovae like their massive counterparts, nor do they fade away quietly like the low-mass stars. Instead, they go through a more measured, predictable life cycle, leaving behind a beautiful planetary nebula and a white dwarf as their legacy. These stars begin their lives in the same way as all stars do, as a collapsing cloud of gas and dust, or a nebula. As the cloud collapses, it heats up, and when the core reaches a certain temperature, nuclear fusion ignites, and a new star is born. For a medium-mass star, this is the beginning of a long, stable phase. The star spends most of its life in this phase, fusing hydrogen into helium in its core. This is the phase our sun is currently in, and it will remain in this phase for another 5 billion years or so. During this time, the star shines steadily, providing a stable source of energy. It's like a reliable old car, chugging along, getting the job done day after day. But all good things must come to an end. When a medium-mass star runs out of hydrogen in its core, it starts to fuse helium into carbon and oxygen. This phase is shorter and more unstable. The star expands, becoming a red giant. It's like a balloon being inflated, growing larger and cooler. The star's outer layers expand, and the core contracts. This phase can last for hundreds of millions of years. During this time, the star can become unstable, pulsating and ejecting shells of gas. This is the beginning of the end for the star. The red giant phase is a dramatic transformation, a star's last hurrah before it settles down into its final form. The star's outer layers are expelled, forming a beautiful planetary nebula. The remaining core, now a white dwarf, slowly cools and fades away, a quiet end to a star's dramatic life. It's a cycle of creation and destruction, a testament to the universe's constant state of change. High-mass stars, the short but spectacular lives of blue giants. In the vast cosmic ocean, high-mass stars, often referred to as blue giants, are the rock stars of the stellar world. These celestial bodies are born from the collapse of massive molecular clouds, much like their lower-mass counterparts. However, their sheer size and energy set them apart, making their lives short but spectacular. Blue giants are typically more than 8 times the mass of our sun, and their immense gravity triggers nuclear fusion in their cores at a furious pace. This process generates enormous amounts of energy, causing these stars to shine brightly in a brilliant blue hue. The life cycle of a blue giant is a whirlwind of dramatic events. In their youth, they burn through their nuclear fuel at an astonishing rate, living fast and dying young. This rapid consumption of fuel means they spend only a few million years in the main sequence phase, compared to the billions of years that lower-mass stars like our sun enjoy. As they age, their cores contract and heat up, igniting heavier elements in a series of fusion reactions. This process creates a layered structure within the star, with different elements fusing in concentric shells. The star's outer layers expand and cool, transforming it into a red supergiant. The end of a blue giant's life is as spectacular as its existence. When the star can no longer sustain nuclear fusion, its core collapses under its own gravity, triggering a catastrophic explosion known as a supernova. This event is so powerful that it can outshine entire galaxies for a brief period. The explosion scatters the star's outer layers into space, enriching the interstellar medium with heavy elements. The core that remains behind can become a neutron star, or, in the most extreme cases, a black hole. These remnants are the final testament to the short but spectacular life of a blue giant, leaving behind a legacy that shapes the future of the universe. Red giants, the swollen phase of stellar evolution. Stars, much like living organisms, have a life cycle. They are born, they evolve, and they eventually die. One of the most fascinating phases in a star's life is the red giant phase. This is when a star, having exhausted the hydrogen fuel in its core, begins to fuse hydrogen in a shell around the core. The star's outer layers expand and cool, giving it a reddish hue. It's like a balloon being inflated, growing larger and cooler. Our very own sun will enter this phase in about 5 billion years. It will expand to engulf Mercury, Venus, and possibly Earth. This swollen phase is a dramatic transformation, a stellar makeover of sorts. During this phase, the star's core contracts and heats up. The increased temperature allows the star to start fusing helium into heavier elements like carbon and oxygen. This process is akin to a chef adding new ingredients to a recipe, creating something entirely new. The red giant phase is a crucial period of stellar evolution, a time when the star is actively creating the heavier elements that make up the universe. It's a cosmic kitchen, cooking up the building blocks of life. Red giants are not just larger, they are also brighter. Their luminosity increases dramatically. However, their surface temperature decreases, which is why they appear red. This is similar to how a dimmer, cooler light bulb might appear redder than a hotter, bluer one. The increased brightness and size make red giants some of the most visible stars in the night sky. They are like the aging rock stars of the universe, still putting on a spectacular show despite their advanced age. Eventually, the red giant phase comes to an end. The star's core becomes hot and dense enough to ignite carbon fusion. For stars massive enough, this leads to a supernova, a spectacular explosion that outshines entire galaxies. For less massive stars, like our Sun, the red giant phase ends with the star shedding its outer layers to form a planetary nebula, leaving behind a small, dense core called a white dwarf. It's a fitting end to a star's dramatic life, a final performance that leaves behind a lasting legacy. White dwarfs, the dense remnants of low and medium-mass stars. In the grand theater of the cosmos, stars play their parts with a dramatic flair that rivals any Shakespearean tragedy. When a star like our Sun reaches the end of its life, it doesn't go out with a bang, but with a whimper, transforming into a white dwarf. These stellar remnants are the dense cores left behind after a star has shed its outer layers. Picture a star as a bustling city, filled with light and activity. As it ages, the city's outskirts are gradually abandoned, leaving behind a tiny, hyperdense downtown that refuses to fade away. This downtown is the white dwarf, a celestial artifact that packs the mass of a star into a volume not much larger than Earth. White dwarfs are the cosmic equivalent of a diamond, small, incredibly dense, and formed under immense pressure. A teaspoon of white dwarf material would weigh as much as an elephant, a testament to the extreme conditions under which these objects form. They are the final evolutionary state of stars that aren't massive enough to end their lives in a spectacular supernova explosion. Instead, they quietly fade away, cooling down over billions of years until they become black dwarfs, though none are thought to exist yet in the universe. The life of a white dwarf is a slow fade into obscurity. Initially, they are extremely hot, with surface temperatures reaching up to 100 degrees Kelvin. Over time, they cool down, their light dimming and their color shifting from blue to red. This cooling process is incredibly slow, taking billions of years. In fact, the oldest white dwarfs in the universe are still relatively warm, as the cosmos hasn't been around long enough for any to cool completely. They are the silent storytellers of the galaxy, their faint glow whispering tales of stars that once were. White dwarfs aren't just passive relics, though. They can have dramatic second acts. If a white dwarf is part of a binary star system, it can pull material from its companion star, potentially triggering a thermonuclear explosion known as a Type I supernova. This is one of the most powerful events in the universe, capable of outshining entire galaxies. It's a fitting finale for a star that once shone brightly, a last hurrah before fading into the cosmic night. In this way, white dwarfs remind us that even in death, stars can leave a lasting impact on the universe. Planetary nebulae, the beautiful final act of sun-like stars. In the grand theater of the cosmos, stars like our Sun often go out in a blaze of glory, creating one of the universe's most stunning spectacles, planetary nebulae. This phase is the star's final act, a beautiful and dramatic farewell before it quietly fades into retirement as a white dwarf. Picture a dying star, having exhausted its nuclear fuel, casting off its outer layers in a spectacular display of light and color. These expelled layers, glowing under the intense ultraviolet radiation from the exposed hot core, form intricate, ethereal shapes that can resemble everything from rings and bubbles to intricate, symmetrical patterns. The term planetary nebula is a historical misnomer coined by Sir William Herschel in the late 18th century. He thought these objects resembled the distant, newly forming planets like Uranus and Neptune, which he had discovered. In reality, they have nothing to do with planets. Instead, they are the remnants of stars similar in mass to our Sun. When such a star exhausts its nuclear fuel, it can no longer counteract the inward pull of gravity. The star's core collapses, and the outer layers are expelled into space at speeds of up to 30 kilometers per second. This process can take tens of thousands of years, during which the nebula expands, and its intricate patterns become visible. The shapes of planetary nebulae are as varied as they are beautiful. Some are spherical, like the famous Helix Nebula, which resembles a giant eye in the cosmos. Others are bipolar, with twin lobes of gas and dust extending in opposite directions, such as the Butterfly Nebula. The diversity in shapes is thought to be influenced by the presence of binary star systems or strong magnetic fields. The colors, too, are a result of different elements present in the expelled material. Oxygen glows blue-green, nitrogen red, and hydrogen a distinctive red. These nebulae are not just pretty to look at, they are also crucial in recycling material back into the galaxy. The expelled elements enrich the interstellar medium, providing the raw materials for new stars and planets to form. One of the most famous examples of a planetary nebula is the Ring Nebula M57 in the constellation Lyra. It is easily visible with a small telescope and appears as a faint, smoky ring. At its center lies the remnant of the original star, now a white dwarf. This tiny, incredibly dense star is all that remains of what was once a star like our Sun. The Ring Nebula is relatively close to us, about 200–300 light-years away, making it a popular target for amateur astronomers. Another notable example is the Cat's Eye Nebula, NGC 6543, which exhibits a complex structure with intricate loops and bubbles. This nebula is about 30 light-years away and is one of the most complex planetary nebulae known. Planetary nebulae are relatively short-lived on cosmic scales, lasting only about 10 years before dispersing into space. Despite their fleeting nature, they play a vital role in the universe's ecosystem. They return enriched material to the interstellar medium, seeding the galaxy with the elements necessary for life. In a very real sense, the atoms that make up our bodies were once part of stars that went through this very process. So, when we gaze upon a planetary nebula, we are looking at the beautiful final act of a star's life, a life that, in a very real way, is connected to our own. Supergiants, the final stage of high-mass stars. In the grand theater of the cosmos, stars play out their lives in a spectacular display of light and energy. High-mass stars, those with a mass at least 8 times that of our Sun, lead short but intense lives. Their final act is a breathtaking performance as supergiants, a stage characterized by immense size, luminosity, and a dramatic end. These celestial behemoths are the heavyweight champions of the stellar world, burning through their nuclear fuel at a prodigious rate. Their cores, under immense pressure, fuse increasingly heavier elements, starting with hydrogen and helium, and progressing through carbon, neon, and oxygen. This is akin to a cosmic bonfire, where each new element requires a higher temperature to ignite, pushing the star to its limits. As a high-mass star evolves into a supergiant, it swells to hundreds or even thousands of times its original size. Picture a star like Betelgeuse, a red supergiant in the constellation Orion, which is so large that if placed in our solar system, it would engulf Mercury, Venus, Earth, and Mars. These stars are not just big, they are incredibly bright, outshining our Sun by hundreds of thousands of times. Their outer layers are relatively cool, giving them a reddish hue, but their cores are furnaces of extreme heat and pressure. The fusion process in these cores is a ticking time bomb, with each new element requiring more energy to fuse. Eventually, the star reaches a point where it can no longer sustain fusion, leading to a catastrophic collapse. The end of a supergiant's life is as spectacular as it is violent. When the core can no longer produce enough energy to counteract the star's immense gravity, it collapses in on itself in a fraction of a second. This collapse triggers a supernova, one of the most powerful explosions in the universe. The outer layers of the star are blasted into space at speeds of up to 10% of the speed of light, creating a dazzling display of light and energy that can outshine entire galaxies. The core, meanwhile, is compressed to form a neutron star or, in the most extreme cases, a black hole. This process enriches the cosmos with heavy elements, seeding the universe with the building blocks for new stars, planets, and even life. In this way, supergiants are not just the final stage of high-mass stars. They are the architects of the universe, shaping the cosmos through their dramatic and explosive deaths. Neutron stars, the ultra-dense cores of dead stars. In the vast cosmic ballet of stellar evolution, neutron stars are the enigmatic dancers that pirouette in the wake of supernovae. These ultra-dense cores are the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. Picture a star several times more massive than our Sun, compressed into a sphere no larger than a city. This is a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons on Earth. The birth of a neutron star is a dramatic event, akin to a cosmic phoenix rising from the ashes of a supernova. When a massive star runs out of fuel, it can no longer counteract the immense gravitational forces pulling it inward. The star's core collapses, and the outer layers are blasted into space in a spectacular explosion. At the heart of this chaos, the core material is crushed so tightly that protons and electrons are forced to combine, forming neutrons. Hence the name neutron star, a stellar corpse composed almost entirely of neutrons. Neutron stars are not just static remnants. They are dynamic and fascinating objects. Some spin incredibly fast, like a cosmic lighthouse, emitting beams of radiation that sweep through space. These are known as pulsars. The fastest known pulsar, PSRJ 1748-2446 AD, spins at an astonishing rate of over 700 times per second. This rapid rotation can create intense magnetic fields, trillions of times stronger than Earth's, which can accelerate particles to nearly the speed of light. The result is a dazzling display of high-energy radiation, visible across the electromagnetic spectrum. Despite their small size, neutron stars pack a powerful punch. Their gravity is so strong that it warps space-time around them, a phenomenon predicted by Einstein's theory of general relativity. This warping can be observed in the orbits of companion stars, or even in the paths of light itself. Neutron stars also serve as natural laboratories for studying the behavior of matter under extreme conditions. Scientists can learn about the fundamental properties of neutrons, the strong nuclear force, and even the nature of the universe itself by studying these stellar remnants. In the grand tapestry of the cosmos, neutron stars are the tiny, ultra-dense threads that weave together the story of stellar death and rebirth. Pulsars, the lighthouse of the universe. In the vast cosmic ocean, stars are born, live, and die in a grand cycle that's as awe-inspiring as it is destructive. When a massive star, much larger than our Sun, reaches the end of its life, it doesn't go quietly into the night. Instead, it explodes in a spectacular event called a supernova. This cataclysmic explosion scatters the star's outer layers into space, seeding the universe with heavy elements. But the core, a remnant of immense density, remains. If the core is massive enough, it collapses under its own gravity, forming a neutron star. And among these neutron stars, some spin rapidly, beaming out radiation like a cosmic lighthouse. These are pulsars. Pulsars are nature's most precise clocks, spinning at mind-boggling speeds. Some complete hundreds of rotations in a single second. They emit beams of electromagnetic radiation, from radio waves to 10th rays, which sweep through space like the beam of a lighthouse. When one of these beams points towards Earth, we detect it as a regular pulse of radiation. This is how pulsars got their name, derived from pulsating stars. The fastest known pulsar, PSRJ 1748-2446 AD spins at over 700 times per second. That's faster than a kitchen blender. The sheer force of this rotation flattens the star, making it more like a disk than a sphere. The discovery of pulsars is a tale of serendipity and scientific curiosity. In 1967, astronomer Jocelyn Bell Burnell noticed regular pulses of radio waves coming from a specific point in the sky. The pulses were so regular that they initially considered the possibility of an extraterrestrial signal. However, further observations revealed the true nature of these objects. Pulsars, with their extreme densities and rapid spins, provide a natural laboratory for testing theories of gravity, electromagnetism, and even general relativity. They help us understand the fundamental forces that govern the universe. Pulsars aren't just cosmic oddities. They serve practical purposes too. They help astronomers measure distances in space, test theories of gravity, and even navigate spacecraft. In fact, the Breakthrough Starshot Initiative, which aims to send tiny probes to the nearest star system, Alpha Centauri, plans to use pulsars as a celestial GPS. Pulsars are also used to detect gravitational waves, ripples in spacetime caused by massive, accelerating objects. In 2017, the Nobel Prize in Physics was awarded for the detection of gravitational waves, with pulsars playing a crucial role in this groundbreaking discovery. So, the next time you see a lighthouse guiding ships safely to shore, remember its cosmic counterpart, the pulsar, guiding our understanding of the universe. Magnetars, the magnetic powerhouses. In the vast cosmic theater, stars are born, live, and die in a spectacular display of celestial mechanics. Among the most enigmatic and powerful actors in this drama are magnetars, the magnetic powerhouses that push the boundaries of our understanding of physics. These ultra-dense, rapidly spinning neutron stars possess magnetic fields so intense that they can distort atoms and emit bursts of energy that outshine entire galaxies. Picture a star with a magnetic field a quadrillion times stronger than Earth's, capable of stripping the electrons off atoms and accelerating particles to near-light speeds. This is the realm of magnetars, where the laws of physics are bent and twisted in ways that challenge our current models. Magnetars are born from the remnants of massive stars that have gone supernova. When a star many times the mass of our Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a cataclysmic explosion. The core of the star, compressed to incredible densities, forms a neutron star. In rare cases, this neutron star becomes a magnetar, its magnetic field amplified to unimaginable levels. The exact mechanisms behind this amplification are still shrouded in mystery, but theories suggest that the rapid spinning of the neutron star and the twisting of its magnetic field lines play crucial roles. It's as if the star's final moments of agony imprint an indelible mark on the cosmos, leaving behind a magnetic monster that continues to wreak havoc on its surroundings. The energy emitted by magnetars is staggering. They release vast amounts of electromagnetic radiation, from radio waves to gamma rays, in powerful bursts and steady streams. These emissions can be so intense that they temporarily disrupt Earth's ionosphere, despite the magnetar being thousands of light years away. Scientists study these bursts to unravel the secrets of magnetars and the extreme conditions they represent. One of the most famous examples is the soft gamma repeater, SGR 180620, which in 2004 emitted a burst of energy that, for a tenth of a second, outshone the entire Milky Way galaxy. This event provided a rare glimpse into the raw power of magnetars and their potential to shape the universe. Magnetars are not just cosmic curiosities, they are laboratories for testing the limits of physics. Their extreme magnetic fields and dense interiors push the boundaries of our understanding of quantum mechanics, electromagnetism, and general relativity. By studying magnetars, scientists hope to gain insights into the fundamental forces that govern the universe. For instance, the behavior of matter under such intense magnetic fields can reveal new states of matter and test theories of particle physics. Additionally, magnetars may play a role in the acceleration of cosmic rays, the high-energy particles that constantly bombard Earth from space. Understanding these processes could shed light on the origins of cosmic rays and their impact on the galaxy. In the grand tapestry of the cosmos, magnetars stand as testament to the universe's capacity for extremes and the enduring quest for knowledge. Black holes, the inescapable gravity wells. In the vast cosmic ballet, stars are born, live, and die in a spectacular display of celestial mechanics. Among the most enigmatic and powerful remnants of this stellar life cycle are black holes, regions of space where gravity's grip is so intense that not even light can escape. These inescapable gravity wells form when massive stars, at least 3 times the mass of our Sun, reach the end of their life cycles. As these stars exhaust their nuclear fuel, they can no longer counteract their own immense gravity. The star's core collapses under its own weight, triggering a supernova explosion that blasts away the star's outer layers. What remains is a core so dense that it collapses to a singularity, a point of infinite density, surrounded by an event horizon, the point of no return. Picture a cosmic whirlpool, a vortex in space where the rules of physics as we know them twist and contort. This is the realm of a black hole, where time slows down and space bends in on itself. The event horizon is the boundary around a black hole where the escape velocity surpasses the speed of light. Once anything crosses this threshold, it is inexorably pulled towards the singularity. Even light, the fastest thing in the universe, cannot escape this gravitational pull. This is why black holes are, well, black. They emit no light of their own, making them invisible to our telescopes. We can only detect them by observing their effects on nearby matter, like the swirling disks of superheated gas and the powerful jets of energy that shoot out from the poles of some black holes. Black holes come in different sizes, each with its own story to tell. Stellar black holes, the most common type, are the remnants of massive stars. They can be as small as 20 miles in diameter, but have a mass up to 20 times that of our Sun. Then there are supermassive black holes, the cosmic leviathans that lurk at the centers of galaxies. These behemoths have masses ranging from millions to billions of solar masses. How they form is still a mystery, but they play a crucial role in the evolution of galaxies. They can regulate star formation, influence the motion of stars, and even shape the large-scale structure of the universe. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, indiscriminately sucking in everything in their vicinity. They are more like cosmic traffic cops, directing the flow of matter and energy in their surroundings. The study of black holes has pushed the boundaries of our understanding of physics. They have forced us to confront the limits of general relativity and quantum mechanics, 2 pillars of modern physics that are fundamentally incompatible. This has led to the development of new theories and approaches, such as string theory and loop quantum gravity, which aim to unify these 2 frameworks. Black holes have also been a testing ground for our understanding of thermodynamics, leading to the discovery of Hawking radiation, a theoretical prediction that black holes can emit radiation and eventually evaporate. This has profound implications for our understanding of the universe, from the nature of black holes to the fate of the cosmos itself. In the end, black holes are not just cosmic oddities. They are key players in the grand symphony of the universe, shaping its structure, driving its evolution, and challenging our understanding of reality. Supernovae, the explosive death of high-mass stars. In the grand theater of the cosmos, high-mass stars steal the show with their spectacular finales, supernovae. These colossal explosions mark the violent end of stars several times more massive than our Sun. Picture a star, a stellar titan, burning through its nuclear fuel at a furious pace. Unlike their smaller, more sedate counterparts, high-mass stars live fast and die young. Their immense gravity and high temperatures allow them to fuse heavier and heavier elements in their cores, forging everything from carbon to iron. But this stellar alchemy comes at a cost. The star's core becomes a dense, inescapable maw, a black hole in the making, while the outer layers, now devoid of the energy that once held them aloft, come crashing down. The resulting rebound is a cataclysmic explosion, outshining entire galaxies and scattering the star's innards across the cosmos. The supernova explosion itself is a complex, multi-stage process. It begins with a shock wave, a titanic pulse of energy that tears through the star's outer layers. This shock wave is so powerful that it can briefly outshine the entire Milky Way galaxy. As it propagates outward, it triggers a chain reaction of nuclear fusion, forging elements heavier than iron, like gold, platinum, and uranium. These newly minted elements are then hurled into space, enriching the interstellar medium and providing the raw materials for new stars and planets. Meanwhile, the star's core collapses under its own gravity, forming either a neutron star or, in the most extreme cases, a black hole. These exotic remnants are the ultimate fate of high-mass stars, their immense gravity warping space-time itself. The aftermath of a supernova is a sight to behold. The exploded star's outer layers, now ionized by the intense radiation of the shockwave, form a vast, glowing nebula. This nebula, known as a supernova remnant, can span hundreds of light years and last for tens of thousands of years. It's a cosmic graveyard, a testament to the star's explosive demise. Within this nebula, the seeds of new stars and planets are sown. The heavy elements forged in the star's core and scattered by the explosion provide the building blocks for the next generation of celestial bodies. In this way, supernovae are not just spectacular fireworks displays. They're also the universe's way of recycling matter and ensuring the continued evolution of the cosmos. But supernovae aren't just important for their role in stellar evolution. They also play a crucial role in the evolution of galaxies. The shockwaves from supernova explosions can trigger the formation of new stars by compressing nearby clouds of gas and dust. They can also regulate the size and shape of galaxies by blowing away excess gas and dust. In this way, supernovae help to shape the structure and evolution of the universe itself. They're a stark reminder of the interconnectedness of all things, a testament to the ceaseless cycle of creation and destruction that defines our cosmos. So, the next time you gaze up at the night sky, remember, those twinkling points of light are not just static, unchanging ornaments. They're dynamic, ever-evolving entities, each with its own story to tell. And for high-mass stars, that story often ends with a bang. Type Ia supernovae, the standard candles of the universe. In the vast cosmic theater, stars are born, live, and die in a spectacular display of celestial mechanics. Among the most dramatic of these deaths are Type Ia supernovae, often referred to as the standard candles of the universe. These stellar explosions are not born from the collapse of massive stars, like their Type II counterparts, but rather from the thermonuclear detonation of white dwarfs. Picture a white dwarf, a dense, Earth-sized remnant of a star, siphoning material from a companion star. As it greedily accumulates mass, it reaches a critical point, igniting a runaway nuclear fusion that tears it apart in a blaze of glory. This process is so consistent that Type Ia supernovae shine with a predictable brightness, making them invaluable tools for measuring cosmic distances. The term standard candle might conjure images of a trusty old lantern, but in astronomy, it refers to objects with known intrinsic brightness. Just as you can estimate how far away a candle is by its apparent brightness, astronomers use Type Ia supernovae to gauge the distances to faraway galaxies. This consistency arises because all Type Ia supernovae originate from white dwarfs of similar mass, ensuring a uniform explosion. When astronomers observe a Type Ia supernova, they can compare its apparent brightness to its known intrinsic brightness to calculate its distance. This method has been instrumental in measuring the expansion rate of the universe, and even in discovering the accelerating expansion driven by dark energy. However, the story doesn't end with their use as cosmic yardsticks. Type Ia supernovae also play a crucial role in the universe's chemical enrichment. As the white dwarf explodes, it scatters heavy elements like iron, nickel, and silicon into the surrounding space. These elements become the building blocks for new stars, planets, and even life. In a sense, the iron in your blood and the calcium in your bones can trace its origins back to the cataclysmic deaths of white dwarfs billions of years ago. It's a humbling thought, a direct connection between the cosmos and our own existence. Yet, the predictability of Type Ia supernovae isn't without its mysteries. While most follow the expected pattern, some exhibit peculiar behaviors, challenging astronomers' understanding. These oddballs, known as peculiar or subluminous Type Ia supernovae, can be dimmer or brighter than expected, or even display unusual spectral features. Unraveling these anomalies is an active area of research, as understanding them could provide deeper insights into the physics of white dwarfs and the mechanisms driving these explosions. Despite these puzzles, Type Ia supernovae remain one of the most reliable and powerful tools in the astronomer's toolkit, guiding our exploration of the cosmos and our place within it. Type II supernovae, the core collapse catastrophes. In the vast cosmic theater, stars play out their lives in a dramatic cycle, and few acts are as spectacular as the core collapse supernovae, also known as Type II supernovae. These cataclysmic events mark the violent end of massive stars, a finale that outshines entire galaxies for a brief moment. Picture a star, at least 8 times the mass of our Sun, burning through its nuclear fuel like a cosmic furnace. For millions, or even billions of years, it maintains a delicate balance between the inward pull of gravity and the outward push of nuclear fusion. But this balance is precarious, and when the fuel runs low, the star begins to collapse under its own immense gravity. The collapse is swift and brutal. In a matter of seconds, the star's core can shrink to a fraction of its original size, heating up to temperatures rivaling the heart of a furnace. This rapid collapse triggers a rebound, a shock wave that ripples outward, tearing the star apart in a spectacular explosion. The energy released is staggering, enough to outshine entire galaxies. This is the birth of a Type II supernova, a cosmic event so powerful it can be seen across vast distances, even with the naked eye from Earth. The explosion scatters the star's outer layers into space, seeding the cosmos with heavy elements crucial for the formation of new stars, planets, and even life. The core left behind after the explosion is a dense, city-sized object known as a neutron star. These remnants are the densest objects in the universe, with a teaspoon of neutron star material weighing billions of tons. Some neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses. These are known as pulsars. In some cases, the core collapse can result in an even more exotic object, a black hole. These cosmic abysses warp space-time itself, their gravity so strong that not even light can escape. The study of Type II supernovae and their remnants provides astronomers with a window into the extreme physics of the universe, offering insights into the life cycles of stars and the very fabric of space-time. The Crab Nebula, a supernova remnant. In the vast canvas of the cosmos, the Crab Nebula stands as a testament to the dramatic end of a star's life. This supernova remnant, located in the constellation Taurus, is the glowing, gaseous aftermath of a stellar explosion that was once a massive star. The nebula is a swirling, luminous cloud of gas and dust, stretching about 11 light-years across. At its heart lies the Crab Pulsar, a rapidly spinning neutron star that emits pulses of radiation like a cosmic lighthouse. This pulsar is a relic of the original star, its intense magnetic field and rapid rotation a stark reminder of the cataclysmic event that birthed the nebula. The Crab Nebula is a celestial laboratory, offering astronomers a unique opportunity to study the life cycle of stars. When a massive star exhausts its nuclear fuel, it can no longer counteract the inward pull of its own gravity. The star's core collapses, triggering a supernova explosion that blasts the outer layers into space. In the case of the Crab Nebula, this explosion was so powerful that it was visible to the naked eye on Earth in 1054 Anno Domini, leaving a record in historical texts. The resulting nebula is a complex interplay of shock waves, magnetic fields, and high-energy particles, all illuminated by the radiation from the central pulsar. The Crab Pulsar is a fascinating object in its own right. It spins at an astonishing rate, completing a full rotation every 33 milliseconds. This rapid spin, combined with the pulsar's intense magnetic field, generates powerful beams of radiation that sweep across the sky like a lighthouse beam. These beams are detected as regular pulses of radio waves, tinth rays, and gamma rays, giving the pulsar its name. The energy from these pulses drives the nebula's glow, creating the intricate filaments and wisps of gas that give the Crab Nebula its distinctive appearance. Studying the Crab Nebula provides valuable insights into the processes that shape the universe. The nebula's complex structure and dynamic behavior offer a window into the physics of supernova explosions and the life cycles of stars. By observing the Crab Nebula, astronomers can better understand the mechanisms that drive stellar evolution and the role of supernovae in enriching the interstellar medium with heavy elements. Moreover, the Crab pulsar serves as a natural laboratory for studying the properties of neutron stars and the behavior of matter and energy in extreme environments. In this way, the Crab Nebula continues to inspire and inform our understanding of the cosmos, a celestial storybook written in the language of light and energy. Stellar recycling: how supernovae enrich the cosmos. In the vast cosmic kitchen, stars are the chefs, and supernovae are the explosive culinary events that stir the pot, spreading ingredients far and wide. This process, known as stellar recycling, is crucial for the enrichment of the cosmos. When a massive star reaches the end of its life, it goes out with a bang, a supernova, ejecting its newly forged elements into the surrounding space. These elements, heavier than the original hydrogen and helium from which the star formed, become the building blocks for new stars, planets, and even life itself. It's a cosmic cycle of destruction and creation, where the death of one star can lead to the birth of countless others. Picture a star as a cosmic alchemist, fusing lighter elements into heavier ones in its core. Throughout its life, it creates elements like carbon, oxygen, and nitrogen, which are essential for life as we know it. But it's not until the star's grand finale, the supernova, that these elements are blasted into space, enriching the interstellar medium. This process is like a cosmic windfall, scattering wealth far and wide. The ejected elements mix with the surrounding gas and dust, forming nebulae that will eventually collapse to form new stars and planetary systems. It's a cycle that has been repeating since the early universe, making supernovae one of the most important processes in cosmic evolution. The elements created and scattered by supernovae are the very stuff of which we are made. The iron in our blood, the calcium in our bones, even the oxygen we breathe were all forged in the hearts of stars and scattered across the cosmos by supernovae. This connection between us and the stars is a profound reminder of our place in the universe. It's a humbling thought, knowing that we are quite literally made of stardust. So, the next time you look up at the night sky, remember that you're looking at the remnants of ancient stars, and that you, too, are a part of this grand cosmic cycle. But stellar recycling isn't just about the creation of life-giving elements. It also plays a crucial role in the evolution of galaxies. The shockwaves from supernovae can trigger the formation of new stars, while also preventing the galaxy from collapsing in on itself. They stir up the interstellar medium, creating turbulence that can both initiate and halt star formation. This delicate balance is what allows galaxies to evolve and change over time. So, in a way, supernovae are the cosmic mixologists, constantly stirring the galactic drink, ensuring that galaxies remain dynamic and ever-changing. It's a complex process, but one that is vital for the continued evolution of the universe. The stellar graveyard, neutron stars, and black holes. In the vast cosmic cemetery, where stars go to rest after their dramatic lives, two of the most enigmatic and powerful remnants are neutron stars and black holes. These celestial objects, born from the ashes of massive stars, are the ultimate recycling plants of the universe, taking the raw materials of dead stars and forging them into something entirely new. Neutron stars, despite their tiny size, are incredibly dense. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. They are the cosmic equivalent of a city packed into a pinhead. Black holes, on the other hand, are regions of space where gravity is so strong that nothing, not even light, can escape. They are the ultimate cosmic vacuum cleaners, sucking in anything that gets too close. Neutron stars are the remnants of supernova explosions, the violent deaths of massive stars. When a star much more massive than our Sun runs out of fuel, it can no longer counteract its own gravity. The star's core collapses, and the outer layers are blasted into space in a spectacular explosion. What remains is a neutron star, an object so dense that its protons and electrons have been crushed together into neutrons. These stars spin rapidly, sometimes hundreds of times per second, and can have incredibly strong magnetic fields. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation that sweep through space like lighthouse beams. These beams can be detected as pulses of radiation, hence the name. Black holes, meanwhile, are the result of even more massive stars. When a star's core is more than about 2-3 times the mass of the Sun, not even neutron degeneracy pressure can hold it up. The core collapses indefinitely, creating a singularity, a point of infinite density, surrounded by an event horizon, the point of no return. Black holes warp space-time itself, creating a gravitational well so deep that nothing can escape. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, sucking in everything in sight. They are more like cosmic speed bumps. Most black holes are relatively small and have a limited influence on their surroundings. However, supermassive black holes, found at the centers of galaxies, can have masses millions or even billions of times that of the Sun. These behemoths play a crucial role in the evolution of galaxies, shaping their structure and influencing star formation. The life cycle of stars is a dramatic tale of birth, life, and death. But the story doesn't end with the supernova. The remnants, neutron stars, and black holes continue to shape the universe in profound ways. Neutron stars, with their intense magnetic fields and rapid rotation, can accelerate particles to nearly the speed of light, creating powerful jets of radiation. These jets can illuminate the surrounding gas, creating beautiful nebulae that glow in 10th rays and other wavelengths. Black holes, meanwhile, can power some of the most energetic phenomena in the universe, from quasars to gamma-ray bursts. They can also merge with other black holes, sending out ripples in space-time that can be detected by observatories like LIGO. In this way, the stellar graveyard is not a quiet, peaceful place. It's a dynamic, energetic environment where the universe continues to evolve and change. The cycle continues, from stellar death to new birth. The universe is a grand recycling system, and stars are its primary components, constantly being born, living, and dying in a never-ending cycle. When a star reaches the end of its life, it doesn't simply fade away into the cosmic night. Instead, it goes out with a bang, shedding its outer layers in a spectacular explosion called a supernova. This cataclysmic event scatters the star's material into the surrounding space, seeding the cosmos with the building blocks for new stars and planets. It's like a cosmic phoenix, where the death of one star can lead to the birth of many others. The material ejected from a supernova is rich in heavy elements, including carbon, oxygen, and even gold. These elements are forged in the intense heat and pressure of the star's core during its life, and in the supernova explosion itself. They are then scattered throughout the galaxy, becoming part of the vast clouds of gas and dust known as nebulae. These nebulae are the stellar nurseries of the universe, where new stars begin to form. It's a bit like a cosmic soup, where the ingredients for new life are stirred together, waiting for the right conditions to spark a new generation of stars. The process of star formation begins when a dense region within a nebula starts to collapse under its own gravity. As it collapses, it heats up, and the center becomes a protostar. This protostar continues to grow and heat up until nuclear fusion ignites in its core, marking the birth of a new star. The remaining material from the nebula may form a disk around the new star, which can eventually clump together to form planets, moons, and other celestial bodies. It's a remarkable transformation, where the death of one star can lead to the birth of an entire solar system. This cycle of stellar life and death has been happening for billions of years and will continue for billions more. It's a testament to the universe's incredible ability to recycle and renew itself. Each generation of stars contributes to the enrichment of the cosmos, making it possible for even more complex structures to form. In a sense, we are all made of stardust, as the elements that make up our bodies were forged in the hearts of stars that lived and died long before we were born. It's a humbling thought, connecting us to the grand cycle of the cosmos. And so, our stellar journey comes to a close, much like a star's life, full of wonder and transformation. We've seen how stars are born from vast clouds of gas and dust, like cosmic seeds sprouting in a celestial garden. They live out their lives, some quietly fading away, others going out in a blaze of glory as supernovae, scattering the building blocks of the universe across the cosmos. Think of stars as the ultimate recyclers. They take simple elements and forge them into the complex atoms that make up everything around us, even the very air we breathe. Every atom of oxygen in our lungs, every atom of carbon in our bodies, was once part of a star that lived and died before our solar system was born. As we look up at the night sky, remember that you're looking at a vast, ever-changing canvas of stellar life cycles. Each twinkling point of light is a story, a journey of creation and destruction, of life and death. And who knows, perhaps one day, the atoms that make up you and me will be part of a new star, continuing this grand cycle of the universe. So, what's next on our cosmic adventure? Stay tuned, because we're just getting started. In our next video, we'll be diving into the mysteries of black holes, those enigmatic cosmic entities that warp space and time. Until then, keep looking up, keep wondering, and remember, you are made of stardust. See you in the next one.